Yes, sir.
Hello.
Yes, sir. Audible.
Yes, sir, audible.
So, good morning to all of you.
Good morning, sir.
Is there any problem? Are you not responding? Am I audible to you or not?
Yes, sir. Audible, sir.
Audible.
Hello.
Sir, audible.
Am I audible?
Yes, sir. Audible.
Yes, I am not getting your voice. Okay. Why I am not getting your voice? I don't understand. Anyway, but if you are audible to me, then it's okay. So then I have to use the chat probably. Hmm. I think you are not getting our voice, sir. Yes, sir. Okay. So, can you say where we left in the last class so that I can pick up from there? Where we have left in the last class? Can you say where I left in the last class? Because I am not able to hear your voice. Please, somebody write in the chat box. Why I am not able to hear you? Please write in the chat box. Are you able to, if you are able to hear me, please write in the chat box where we left in the last class. Okay, so that I can
So
start
example
from there.
6.10.
Example, example 7.7. Okay, so a glider with mass m is equal to 0.200 kg sits on a frictionless horizontal horizontal track connected to a connected to a spring with force constant K is equal to 5.00 Newton per meter. You pull on the glider. You pull on the glider, stretching the spring, stretch, stretching the spring 0.100 meter, and then release it with no initial velocity. The glider begins to move back toward its equilibrium position. That is x is equal to 0. What is its x velocity when x is equal to 0.80 meter. Okay. 0.0, sorry, this is 0.80 meter. Okay. Example 6.10 done. Oh, what about chapter 7? Yes, we not started chapter 7? Why I am not able to listen to you? That is the big
No, sir.
problem. So, have we not started chapter 7? Okay, okay, okay. So this is chapter 7. So first we will start out gravitational potential energy. Okay. So gravitational potential energy. So this is chapter 7. I'll write. So we'll start with then this is, let me put it here. This one, this example will come later. So in chapter 7 is gravitational potential energy. Okay, chapter 7 is, just wait, it is potential energy and energy conservation. 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 So first we will learn about gravitational. So this topic, there are 4 topics, and the topics are gravitational potential. Topic 1, gravitational potential energy. Gravitational topic 7.1, gravitational potential gravitational potential energy. Okay, so we'll learn about gravitational potential energy. So I will give you 2 examples. Okay, um, just what are the examples? First we will take how we are going to, what is gravitational, what is potential energy, and what is gravitational potential energy, and how we are going to relate this gravitational potential energy with work done. Okay, so I will take 2 cases, one a body falling down and another a body moving off. First I will find out body falling down. So you just see body falling down. Okay, so suppose a body is at this position. Suppose this is your horizontal, y is equal to 0. This is y is equal to 0. And your body was at this position. Suppose this is your body. It was at this position and this distance is y1. This is y1. Okay. And the body falls down and it comes to this position. Okay, and these positions, and this is y2. This is y2. Okay, and the force is acting like this because this is the weight of the body, because if the body has a mass m, then the weight is acting vertically downwards. This is W is equal to only mg. If I will write with the direction, then W is equal to minus mg. So you know this force is constant because now I can write the magnitude of this force is equal to mg, which is constant because g is a constant. So my work done will be Fs cos theta or Fs cos phi. Fs cos phi. Okay, because you see the displacement is also in the same direction, isn't it? What is the displacement? y2 minus y1. y2 minus y1 is the displacement, and you have to put a minus sign because it is in the negative direction. This is your displacement. If I write this displacement with a vectorial notation, then this will be my displacement. But these are the magnitudes I am using. Okay. And similarly, my force, if I will use it, is minus mg. But this is a notation. So the magnitude of F is mg. the magnitude of S has to be positive, but y2 is less, y1 is bigger. So the magnitude will be y1 minus y2. y1, because the magnitude has to be positive. That is the magnitude of the displacement, y1 minus y2. And because they are in the same direction, this S and F, this is your force and this is your displacement. They are in the same direction. So your cos phi is cos 0 degree. Okay, cos 0 degree is 1. So you get, sorry, in this place, in this S, um, this is, oh, sorry, I will write, this is the magnitude is y1 minus I2. I should have written it because this is S. So mg is the magnitude of force. The magnitude of S is y1 minus y2. So I will write it here, y1 minus y2, y1 minus y2, and cos phi is cos 0 degree, cos 0 degree. Okay, so I will get mg y1, mg y1 minus mg y2, minus mg y2. Now suppose the body has fallen to the ground. Now in that case y2 will be 0. So this part will become 0, isn't it? And because this is the work done by the gravitational force, so I must write W grave. Okay. Now you see, as I was telling you, if the body would be falling to the ground, then y2 will be 0. So if y2 is equal to 0, then the work done by the gravitational force in taking a body from a height y1 to 0 will be mgy, mgy. Okay, so this is the work done by the gravitational force. Now this work done is actually the potential energy. We have to identify it as the potential energy. As you have identified half mv square as the kinetic energy, similarly the gravitational potential energy is identified as mgy. Pe is potential energy. So once you have identified the potential energy like this, then mgy1 will be your gravitational potential energy initial. So u1 grave, you have to write it as u1 grave, and similarly write the other as u2 grave, the final gravitational potential energy. But you know u2 minus u1 is delta E, so you can write this W grave, you can write W grave is equal to W grave is equal to minus u2 grave minus u1 grave, or that is equal to delta U grave. So here you get a different equations. You know that the total work done is equal to change in kinetic energy. W total is equal to delta K. But here the work done by a gravitational force is equal to negative change in gravitational potential energy. Okay, so that is the basic difference. So what does that mean? Before going to that part, let me find out what will be this equation for a body going up. This is we have found out for a body falling down. Now I will find it out for a body um, moving up. So how I am going to do that? So body moving up. Let us see what happens. Again, I have to find out this for a case where the body is moving up. Oh, body moving up. So when a body moves up, the initial position is y1. That means it moves from this position y1 to a higher position, higher height, y2, isn't it? It will move to y2. Okay. Now in that case, what will happen? Just you see, now the displacement is in the positive y-axis or upward, but the weight is acting downwards. So the angle phi between the displacement and the force is now 180 degree, not 0 degree. Okay, so you see this force that is mg is acting vertically downwards, but now the displacement is not acting downwards, but it is acting upwards. So look at the angle, they are now 180 degree apart. So phi is equal to 180 degree. Okay, so when I will find out my work done, W is equal to Fs cos phi. F is the magnitude of the force, which is minus mg. S is the magnitude of the displacement, and cos 180 degree. Cos 180 degree. So in place of F, I will write its magnitude as mg. And what is my displacement? It is y2 minus y1, and y2 is bigger, y1 is smaller, so there is no problem. I can write the magnitude as y2 minus y1. Okay, and cos 180 degree is minus 1, so I will put a minus 1 here. So this becomes mg y1, mg y1 minus mg y2, mg y1 minus mg y2, mg y1 minus mg y2, isn't it? So now we get mg y1 minus mg y2, which is again negative change in the potential energy. Okay, because we have already identified mgy1 as the gravitational potential energy at the point y1, and mgy2 is the gravitational potential energy at the point y2. So I will write it as, just wait, I will write it as gravitational potential energy point 1, because it is gravitational, so I will mention GRAV, gravitational, and then minus U2, again I will mention GRAV. Okay, but you know U2 minus U1 is delta U, so I can write it as minus delta U, isn't it? Minus delta U grave. Okay, so work done, and because this work is done by the gravitational force, so in order to distinguish it from others, I will write W grave is equal to minus delta U grave, isn't it? Delta U grave. So we saw that whether the body is moving down or whether the body is moving up, the work done by the gravitational force is always equal to negative change in gravitational potential energy. What is its physical implications? Now let me tell you. What is the physical implications? And from here, how can we go to the conservation of mechanical energy and total mechanical energy? A new concept will be found out. So the next part is, just wait. Okay. So we know that W total in chapter 6 we have seen that W total is equal to delta K. W total is equal to delta K. And W grave, just now we have found out, both for body falling down and both for body moving up is equal to minus delta U grave. Suppose that the only force that is acting on the body is gravitational force, and that is the only force which is doing work. Then you can write that your W total is equal to W grave. W total is equal to W grave. If only gravitational force is doing work and it is the only force that is acting on the body. Then what you can write? Then you can write that delta K is equal to delta K is equal to minus delta U grave. Delta U grave. Okay, delta K is equal to minus delta U grave. Now what will happen? You see, gain in kinetic energy is loss in potential energy, and loss in kinetic energy is gain in potential energy. And how you are going to interpret it physically? When you are throwing a stone upward, the kinetic energy gradually decreases and the potential energy increases. But when the same stone falls downward, the potential energy decreases and the kinetic energy increases. That means one is increasing or decreasing at the cost of the other, so that naturally your energy is not wasted. It is being converted into one form to another form. And because when I will bring this delta U grave to this side and take delta common, then inside the bracket I will find out K plus U grave. K plus U grave. And K plus U grave is nothing but now that is equal to the total mechanical energy. So I can write my K plus U grave this as the E, and E is my total mechanical energy. I can write this because total mechanical energy is the sum of kinetic energy plus gravitational potential energy when only the gravitational forces is present. So this is total mechanical energy. Total mechanical total mechanical energy. Total mechanical energy. Total mechanical energy. Okay, so from here we can write that delta E is equal to 0. What does that mean? Delta E is equal to 0. That means delta E is E2 minus E1. So E2 minus E1 is equal to 0. So E2 minus E1. E2 minus E1 is equal to 0, or E2 is equal to E1. What is E2? E2 is the initial kinetic energy plus initial gravitational potential energy, sorry, E1 must be equal to final kinetic energy plus final potential energy. That means I can write this equation as, if I want to write the and this is what is called conservation of energy, that is half mv1 square, half mv1 square plus u1 grave. That means the gravitational potential and initial gravitational potential energy, u1 grave. u1 grave is equal to half mv2 square, final kinetic energy of mv2 square plus final potential energy u2 grave. u2 grave. So this is u2 grave. Okay, so we see that the gravitational potential energy is always equal to, the work done by the gravitational potential energy is always equal to the negative change in the work done by a gravitational force is always equal to the negative change in gravitational potential energy. And from there, we find out that the gain in kinetic energy is equal to loss in potential energy, or loss in kinetic energy is equal to gain in potential energy. But the gain in kinetic energy plus loss in potential energy is always zero, because the total energy remains constant when only the gravitational forces are acting on a body, isn't it? Now we'll come to the next part. That is, so I have drawn 7.1 for you, and 7.2 will be that 7.2. Just wait. Um, 7.2 will be, it is 7.2, elastic potential energy. Then we will go to another form of potential energy, elastic potential energy. Now you know about the gravitational potential energy. So when gravitational force is associated, when the gravitational force is associated, a gravitational potential energy is there. And so gravitational potential energy, when, can say, when gravitational forces are present, gravitational potential energy is there. Gravitational potential energy is there. Similarly, here I will show you that when elastic forces are present, when elastic, or that is also known as spring force, SPRING, when elastic forces are present, also another potential energy known as elastic potential energy is present. Elastic potential energy is present. And we know our gravitational potential energy, we have also represented it as gravitational U grave. I can show this U grave. Okay, U grave is equal to mgy. You are familiar with this equation, because in place of y we are taking mgh, isn't it? So this is U grave. Similarly, I will also find out an expression for elastic potential energy. Before that, what we are going to do, let us see. Now suppose there is a spring. Okay, let us say there is a spring like this, and this spring is relaxed. That means you are not either compressing it or you are pulling it. So it is in the relaxed state. Okay, so there is no displacement, relaxed. When you try to, either, suppose there are two things, either if you try to compress it, suppose you want to compress it, now you have compressed it. If you compressed it, then there will be a restoring force which will act in this direction, opposite to your compression. You are providing compression in the negative x-axis, the restoring force will act in the opposite axis, opposite or positive x-axis. Suppose you are trying to stretch the spring like this. That means you are applying a stretching force in this direction. Then the restoring force will be opposite to it. So it will act in the negative x-axis. That means the objective or the business of the restoring force is to bring back the spring from the stretched or the compressed position to the relaxed position. That is very important, that you must understand. And that restoring force is called, is governed by Hooke's law, because that is an empirical law. So F is equal to minus Kx. You know, I have already introduced you to these equations, where x is the displacement from the relaxed position or mean position, that is also called the mean position. So I can write my x as displacement from the mean position or the relaxed position. Displacement, okay, from the mean position. Displacement from the mean position. Displacement from the mean position. Displacement from the mean position. Okay, and k is your spring constant. K is equal to spring constant. Now suppose you want to, when you are stretching the spring or you are compressing this spring, you are applying an external force equal to the restoring force. Otherwise, you cannot stretch or you cannot compress. Okay, so the restoring force is equal to minus kx, but the external force, F external, is equal to plus kx, isn't it? That you must understand. F external is equal to kx. So let us find out what is the amount of work done by this restoring force when you stretch a spring from x1 position to x2 position. That means the relaxed position is x is equal to 0. Suppose this position is x1. From here again you stretch it to further. So you are stretching it from x1 to x2. Okay. Then what is the amount of work done by the external force? What is the amount of work done by the restoring force? First, I will find out the work done by the restoring force. So how I will find out? W elastic, because now my elastic force is doing work. So W elastic, and this is a variable force. Remember, earlier the mg force was a constant force. So I cannot find out my work done by multiplying the force with the displacement. Okay, so what I will do? I will do an integration from x1 to x2 of the f dx. Okay, f dx. So I will do a like this, f dx. So what I will get? I will get, in place of x, I will write minus kx dx minus kx dx integral x1 to x2. x1 to x2. Okay, so I will find out just wait. And that is equal to minus k integral x1 to x2 x dx x dx. So that is equal to, if I do the integration, then I will find out minus half kx2 square, kx2 square, okay, minus plus half kx1 square, half kx1 square, kx1 square. Okay, so I find out my elastic, the work done by my elastic force is equal to, in stretching a spring from a position, initial position of x1 to a final position x2, is given by WEL. WEL is equal to half kx1 square, half kx1 square minus half kx2 square. Half kx2 square. Okay. So if you are pulling the spring from the relaxed position to the final position, suppose that means if the initial position x1 is equal to half kx1 square minus half kx2 square. Okay, this is the work done by the elastic forces. Just wait. So first let me find out the equations. So now what I will do, I will identify that half kx1 square is the elastic potential energy U1 EL. U1 EL, okay, minus U2EL, U2EL, and which I can write it as change in the minus change in the elastic potential energy. Okay, elastic potential energy. So there is a deep relationship between the gravitational forces and the elastic forces, because I got the same thing. The work done by gravitational forces, is also equal to negative change in the gravitational potential energy. There is a potential function whose negative change is equal to the work done by the gravitational force. Similarly, W elastic is also work done by the elastic force is also equal to minus delta UEL. Okay, elastic. Okay, so, and we will see that actually there is a deep connection between these two forces, and they constitute a separate type of forces which we will discuss in the next class, and they are known as conservative forces. Because they are conservative forces, that's why you are getting conservation of energy when either only gravitational forces are present or when only elastic forces are present. Suppose only elastic forces are present, then what happens? Let us see. When only elastic forces are present, then your W total is equal to WEL, because the total work is now being done by the elastic force. So you can write W total is equal to W elastic, isn't it? But you know, according to work energy theorem, that W total is equal to change in kinetic energy. So W total is equal to delta K. And just now we have seen that WEL is equal to negative change in the potential energy. Okay, delta UEL. Okay, so in place of, so I can write W total means del K is equal to minus del UL, minus, similarly the same thing. Gain in kinetic energy is loss in the elastic potential energy, and loss in the kinetic energy is equal to gain in the potential energy, elastic potential energy. And so delta K plus UL, you can write K. Here your potential energy is elastic potential energy, K plus UEL. Here also the total E will be the total mechanical energy, and this will be 0. So your delta E is equal to 0. Total mechanical energy is equal to 0, or U1 is equal to U2, or the energy is conserved. Okay. Now we'll go to the next important thing. Suppose many forces are present. The gravitational forces present, elastic forces present, and other forces are also present. Then what will happen? Let us see. Okay, so now three categories of forces are present, and elastic forces, gravitational forces, and other forces like the frictional forces or the external applied force. Then how we are going to get our equations? Okay, so the next part is, suppose gravitational forces is present. So I will write GRAV, gravitational forces are present. Gravitational forces are present. That means gravitational forces is present. Gravitational forces is always present because the body has a mass, means it has a weight. And elastic forces are present. Elastic forces are present. And other forces are also present, like frictional forces or any other type of forces, applied force like this. Other forces are also present. Then my work done, W total, will now consist of sum of three quantities. What are they? Work done by the gravitational force, isn't it? Work done by the gravitational force plus work done by the elastic force plus work done by other forces. Work done by other forces. Okay. But you know that W total is equal to delta K according to work energy theorem. And now we have found out that W grave is equal to minus delta U grave. So you can write it minus delta U grave. And you find your W elastic is equal to minus delta U EL. Delta U EL. Okay, plus W other, plus W other. Okay, so now we have got the equation like this. Now what will happen? So the change in kinetic energy or gain in kinetic energy is equal to loss in the potential energy. Now what I will do? The right hand side I will put minus del like this, and then U grave plus U EL I will put inside the bracket because they are different types of potential energy. U grave plus U EL. This is EL. EL means elastic plus W other, work done by other forces like your applied force or frictional force like this. W other. So that is equal to minus delta U. So now your potential energy consists of two terms, gravitational and elastic, and you write it as plus W other. Now what I will do, I will take this potential energy terms to the left hand side. So this will delta K plus U. K plus U is equal to W work, W other, work done by other forces. Okay. Or delta E is equal to W other. W other. So how your delta E is going to behave? The next thing is how delta E will behave. Now delta E will be 0 if W other is equal to 0. That means if no other forces are present, then your initial total mechanical energy is equal to final total mechanical energy. So this will give us three cases. W other, when the work done by other forces is equal to 0, this implies that the initial total mechanical energy is equal to the final total mechanical energy. And what is your initial total mechanical energy? It consists of three terms: half mv1 square plus mg. So if I will write it, actually, you see I am writing it so that you will understand. So how I am going to write it? U1. So U1 will be K1. So what will be K1? Half mv1 square. Half mv1 of mv1 square. And what will be my u1? U1 will be gravitational potential energy, mgy1. Mgy1 is the gravitational potential and initial gravitational potential. What will be my initial elastic potential energy? Half kx1 square. Half kx1 square. Okay. this must be equal to the final sum of final kinetic energy half m v2 square half m v2 square plus mz y2 plus mz y2 mz y2 plus half kx2 square half kx2 square half kx2 square. Okay, so this is how you can write your total conservation of total mechanical energy when no other forces are present. So the work done by other forces is zero. That's why you are getting the initial total mechanical energy is equal to final total mechanical energy, or the whole expression will look like this. This is case 1, isn't it? This is case 1. Now case 2 is when W other is not equal to 0 and it is greater than 0. Suppose W other is greater than 0. That means you are doing work on the body. The other forces is doing work on the body, positive work on the body. In that case, what will happen? E2 will be greater than E1. E2, because E2 will be greater than E1. Okay. That means half mv2 square plus mgy2 plus half kx2 square will be greater than half mv1 square plus mgy1 plus half kx square, kx1 square by w other amount. That means you can write that this will be equal to this plus w other. The third case is when W other is less than 0 or negative work is performed by the other forces like frictional forces. Then U1 W other is negative. In that case, what will happen? That implies that E2 is less than E1. E2 is less than E1. So how you are going to write the full expression? You will write that half mv1 square plus mgy1 plus half kx1 square minus w other is equal to this much, or half mv1 square plus mgy1 plus half kx1 square is equal to half mv2 square plus mgy2 plus half kx2 square plus w other. Okay, so the total energy is W other amount smaller than U1 when W other is less than 0. So these are the three cases. So now we see that when gravitational forces or like conservative forces like gravitational or elastic forces are present, then the equations assume different forms. Okay. So now you understand three things. One is the gravitational potential energy can be expressed as W gravitational is equal to mg y or mgh. Your h is y here, mg y. And elastic potential energy is expressed as half kx square, isn't it? Half kx square. This is elastic potential energy. Now this behavior, elastic potential energy and gravitational potential energy, are associated with conservative forces that you will see in the next class. So maybe I will give you a conclusion or the summary of whatever we have learned. Unfortunately, I am not able to hear you. So initially what we did actually, sir, please tell the syllabus at UPM for mid-semester examination. Will chapter 7 also in the syllabus for mid-semester? I don't know. I do not know. I can tell you maybe after a day or two. Okay. So now the summary is like this. People are very much worried about the syllabus and all these things. So we have discussed about gravitational potential energy, gravitational, what is the work done by the gravitational force, and we find out that the work done by the gravitational force W, uh, I can also write this W grave, work done by the gravitational forces, work done by the gravitational forces, work done is equal to, work done by the gravitational force is equal to minus delta U grave, isn't it? Minus delta G or a V minus delta U grave. Okay, this is the uh, expression for the potential energy. So I can write it as U grave. I can this let us bring one. So U control C. So this side. Okay, so U grave is equal to mgy and W grave is equal to minus delta U grave. Similarly, in case of the elastic potential energy also, I write this U elastic. I can write the whole equation, these two equations as also I can write U elastic. U elastic is equal to half kx square, isn't it? This I can write it as 1 2 then k and x square, half kx square, isn't it? And W elastic, this W elastic can be written as minus delta UEL. Okay, so work done by the elastic forces is equal to negative change in the elastic potential energy. So these two things we have already derived, isn't it? So I hope in the next class we will be reading about different examples before going to conservative and non-conservative forces. So what are the chats here? Okay, so this part, let me, I don't know. Okay, so somehow why I was not able to listen to you. Anyway, so I think uh, we should stop here because I have already told you about how to calculate the gravitational potential, work done by the gravitational force and work done by the elastic force, and what is conservation of energy. Yes, so the last also this we did, that E is equal to this, E is equal to this total mechanical energy. This total mechanical energy is equal to K plus U. K plus U. Okay, U can be a sum of elastic and the potential, gravitational potential energy. This U can be UEL. This can be UEL plus U gravitational, isn't it? This U plus, this is, just wait, this is plus U gravitational Z or A B, isn't it? So U is equal to U grave plus U EL. So this is how we can work out different things, and we see that this total energy is equal to and the work, another thing we find out that this E2 is equal to, control C, I can also write, if there are other forces, then E2, this can be written as E2, isn't it? This will be E2 E2 is equal to E1 plus, okay, this will be E1 plus W other. Okay, this will be W other. Now, when the work done is positive, E2 is greater than E1, isn't it? When work done W other is equal to 0, then E2 is equal to E1. And when W other is equal to negative, E1 is greater than E2. So this is how, or you can also write this as E2 minus E1. You can put a equality here also. W other is equal to